Yes, coffee is sort of to set a general tone for how to view these results, not as a research paper being presented in 15 minutes, but something which is intensive. So the idea of the summer workshops is actually quite old. It started in 93 at Rutgers University. It was held for 2 years there. And in 95 it moved to Hopkins, and we've been having it here since then. And it's a bit scary when I count it up. This is the 7th workshop we're having in Hopkins. It's a fairly long series. So we can pretty much stand up and claim, yes, we have a tradition here. And what was the idea of these workshops? The idea was to basically do some fun research in education. And when I say education, I'm not just talking speeches to students. I'm talking one researcher to another. And so the idea was that we would have, we'd bring together interesting people from different places and have them work on specific problems. And they started off with mainly DoD wanting to solve switchboard. And they got together pretty much all their contractors and everybody who was working on switchboard into one room, locked them up for 6 weeks, and hoped that something nice would come of it, and it did. And since then we have grown and started looking at problems other than speech recognition. And since then our sponsorship has also become diverse, and now it's not just DoD, but DARPA and NSF. And this year's team will, of course, show you the goals of the diversity, one working on speech and the other working on text. But one example I like to give is the team in 99, where we had one team working on speech synthesis, one on recognition, one on text processing and discourse modeling, and one on information retrieval. We pretty much had a broad spectrum of coverage. So like I said, we usually organize these groups in this workshop into 3 or 4 focus groups, each working on a specific topic. This year you'll see we have only 2 groups because we had slightly less funding this year. But nonetheless, we had 2 very different topics. The way these topics get selected, I'll tell you a little bit more about that in a minute. Basically, we go about soliciting proposals from various people all over the country, and then we have something like a peer review meeting, which lasts about 2.5 days, where we look at the proposals, debate them, try to shape them, make them even better than what they are, and then in the end, people vote on it and pick up a topic. And of course, the whole effort starts way back in the fall, and all through the spring, the teams are preparing for these for the 6-week workshop. And then, like I said, there are 2 weeks where you have intense training for the students to kind of get them ready for these research proposals. So how do these topics get selected? Well, we kind of make a very broad call for proposals, and we did this year, for example, for this year's workshop in September last year. We sent them to all sorts of mailing lists to all the people we know in the field, advertise them at conferences and workshops. We also ask all our program managers to suggest people who would suggest good topics for workshops. And finally, we kind of contact all the heads of IBMs and AT&Ts and CLUs and MITs and so on, and tell them, look, if you have people with good ideas, tell them to send proposals. And then we vet the proposal just a little bit. We look at things which are completely infeasible in the 6-week workshop. But most of the ideas are actually quite interesting, and then we put them in. There's only one stipulation. People who send these proposals are told that if your proposal gets selected, you have to be in the summer at Hopkins for 6 weeks. And so it means that nobody's just going to tell you, well, this is a cool idea, go work on it. They themselves, and we found that this is a real way to make progress because if people really believe in an idea, they want to work on it. And this gets us, like, not only does it get us good ideas, it gets us the best people to work on that idea, the best proposals and concepts. And finally, we take all these ideas together and have a conference. This time it was held in Airlie in Virginia and Washington. And basically it's a bunch of, the authors are invited, and then the program manager and a few other people who are gone there, and like I would say, for their wisdom and their expertise, the senior researchers. And a debate and a discussion takes place in the last 2 days. Some of you have been for that meeting. And at the end of it, we come up with a sort of more consolidated or more distilled proposals which are more suited to an attack in this workshop environment. And then people vote on it. And the criteria that I use, or that we instruct people to use, are scientific merit. We want to have proposals which are well-founded. We want to use this opportunity. What the workshop has to offer, which is unique, is this collaboration. You can get 5 different people from 5 different universities with different skills to work on this problem. So if a particular problem can take advantage of that, that should get more points, because after all, this is about collaboration. Of course, we want to solve important and interesting problems and not something that is just esoteric and of interest to a small group of individuals. Basically, we're looking for societal impact here. Will solving this problem really help people at large? Finally, this year we had a theme on multilinguality because we were, like, a lot of programs that were supporting the workshop were interested in multilingual language processing capabilities, so that was one of the criteria we used. And finally, we wanted something that would be feasible in a 6-week workshop preceded by 6 months of preparation. And so we picked something for which, for example, there were either data resources available or which could be made available in the 6 months leading up to the workshop. So this led to the selection of 2 teams, and here is the first one. And I've put up their nominal title, Automatic Summarization of Multiple Multilingual Documents. It's led by Dragomir Radev, who's sitting here, who's at the University of Michigan, and the other senior members in the team. And let me just use this to do the introductions are Simone Teufel from Columbia University, who is now going to be at Cambridge University in England. And Horacio Sarjan, who is over there, from Sheffield, Professor Wai Lam from the Chinese University of Hong Kong. The graduate students in this group are Elliot Drabeck from Johns Hopkins, Daniel Liu from Chinese University of Hong Kong, who's now going to be at Alabama, and finally Hong Shi from University of Michigan. And of course, one of the things we do in these workshops is we recruit undergraduate students, and we hope that this workshop will be enough big that they'll now dedicate the rest of their careers to human language technology. Some of them come to universities, others go into the workforce, still others go to Wall Street to make money, but we get most of them. And this year we are Arda Chalebi from Bilkent University. He came to us from Kemal Al-Azhar, and John Blitzer from Cornell University. He came to us from Clare Cardi. The second team, and here I must apologize even before you start reading the list, I left out 2 people in my hurry to make the slides, so I'll mention them as I go along. The team leader is Jeff Burns from the University of Washington, and Jeff is probably still making his last couple of slides, and Jeff's right from IBM. Okay, that's why they chose the afternoon presentation. Thomas Richardson, also University of Washington, he's a statistics professor. Eric Sandnes, who had to leave yesterday, he's from SpeechWorks. Kurt Jackson from DOD, there he is. And the graduate students are Peng Shu from Johns Hopkins, Karen Levescu from MIT, Karen, she's in the back, and Karim Filali from the University of Washington. And the undergraduates in this group are Jerry Torres from the Symbolic Systems group at Stanford, and Eva Holmes, who does linguistics at Harvard. And the 2 people I left out in my hurry are Yigal Brandman, who's sitting back there at PhoneTax. He should count as one of the senior members, and Bill Byrne, who provided a lot of expertise to this group. Bill, of course, is very familiar to all of you. So this slide will change by the time it goes into the final report. Okay, the 2 weeks before the workshop, we had a sort of a crash course on speech and language technology for all the students. And let me just quickly tell you what went on over there, since we are sort of in the business of reporting and all the things that happened.
we had 9 days, one day with a theme on each day. So the first day's theme was speech recognition principles and applications. I gave sort of an overview lecture, but the highlight was Gish from BBN, who brought the Oasis system. I believe it now has a new name called On Tap. So it used to be Rough and Ready, then it became Oasis, and now it's On Tap. Then we had a speech signal processing day when Joe Piccone came over, talking about the front-end business that goes on in speech recognition, used the public domain tools that he has prepared to kind of give them a hands-on lab on how to build speech recognizer and how to play with the front-end in speech recognizer. Yigal talked about the speech recognition features that he has developed. We had an information retrieval day. We had James Allen from UMass and Gina Levaux from the University of Maryland. They talked about information retrieval across lingual IR, and they put up this nice lab where the students, again, actually sat down with the database and built an IR system and played with it. So as you can see, what's happening is that all the students are getting a little bit of everything, and as you can see, in 2 weeks, they'll be familiar with across-the-board human language technologies. Then we had a natural language processing day. We had Phil Resnick from the University of Maryland and Srinivas Bangalore from AT&T. They talked about tagging, parsing, and NP bracketing, and they also had a lab where they again used data and statistical methods to build fairly sophisticated NLP modules. We had machine translation by David Yarowski, and we had Kishore Pakuneni come and talk on the same day from IBM about IBM's work on machine translation, in particular to kind of throw the idea around that machine translation is not about translation as we know it, but many other things. For example, translating a natural language query into SQL so that you can then access a database, it turns out can be solved very nicely by thinking of it as a machine translation problem, and so on. And again, David set up a very nice lab that they used the Giza toolkit developed 2 years ago to actually build a translation system. We had a day on text summarization. Again, the idea is that although the students are assigned to 2 groups, they learn about both the groups. And in the GP from NITER, Vasilios Vassiliou from Columbia and Simone gave lectures, set up a lab. People actually did summaries by hand, tried to see how summaries get evaluated. We had a day on the anatomy of speech recognition. That's the best title I could put on it because we had 2 different things we did that day. Bill Byrne had them build a whole speech recognition system from start to end using the research management toolkit, which is available with the HTK software. So each of these students in this room has actually built a speech recognizer by themselves. And Professor Eric Young, who is in our DME department and very well known all over the world for his work on auditory physiology, talked about how the human ear works. So we have the anatomy of both the machine recognizer and the human recognizer. Of course, at Hopkins, we pride ourselves on all the diversity we have in the human language arena, so not just the engineering, but the science. So we had Peter Jusek from psychology talk about how children acquire language. We had Paul Smolenski talk about the cognitive aspects of language, and he's of course known all over the world for his work on optimality theory, so he talked about how basically you can explain our ability to acquire language, or at least go towards it by thinking of a set of constraints and violations, and different languages just organize these constraints differently. And of course, we had Victor Zhu's spectrogram reading class. We didn't get Victor Zhu this time. We did a couple of years ago and last year. This year we had PJ Hazen from MIT, who was on the research staff there, coming pretty much to that lecture. So again, the students in this room can now read spectrograms. And finally, we had Jeff and Jeff, as we've started calling them, give these students a series of lectures and a lab on graphical models, what the basic ideas are, and how to actually use the toolkit that they have developed. And you can imagine what this kind of bombardment does to the minds of young people over 2 weeks. So by then they were completely saturated. So we of course had an escape clause in there. This is the week of 4th of July, so we all went down to Washington. We saw the museums, we joined the DC Folk Festival, and we had a lot of fun. And then of course, the grown-ups arrived. So this is July 9th now, we are moving forward in time, and this is the first day of the workshop. And at this point, I will stop and I'll just let the senior people tell you what all happened. The day is organized into 2 parts. Drago is going to talk in the morning about the summarization group. And when I say Drago, I mean he and all his teammates. And then we're going to break for lunch, and then we resume. Jeff and Jeff will talk about the graphical models. Drago, thanks.
everybody. As you know, Jeff is still having his slides, so we went first. But that didn't mean that we didn't have until the very last moment to prepare ours. So you will notice occasionally some disturbances here and there, but I hope you will understand and excuse us. Okay. So first of all, what is summarization? Most people have seen abstracts of different kinds. For example, Cliff's Notes or sound bites on TV and so on. It turns out that summarization has been researched for about 40 years now, and still most of the most interesting accomplishments have been made over the last 5 or 6 years. And summarization deals with several distinct problems which have their own idiosyncrasies. So one of them is single document summarization. That is when you take as input a piece of text and you try to extract the most important information in that document. The next one is cross-lingual summarization. You extend a single document case to the situation where you have documents in one language and you want to produce a summary in a different language. You also have multi-document summarization, which deals with several documents which are related somehow to each other, and then you want to produce a single document out of them. Another shade in the spectrum of summarization is query-based summarization. So, suppose you have a single document and different users with different needs. How can you produce summaries that meet the needs of all the different users? Now, one of the ways to do this is to have users specify a certain query, and then depending on their query, get different summaries. And finally, a very important problem in summarization, research in summarization, is how do you evaluate summaries? How do you compare two summaries? How do you compare two systems that build summaries? How do you compare systems with humans? Okay, so we try to address some portions of all of those problems. And here's what we did. We acquired a corpus from LDC that contains a large number of English language documents. And our goal was to be able to produce single document summaries from individual documents. Then we also acquired, again from LDC, Chinese translations of those documents. And the assumption was that for each English document we know the corresponding Chinese translation. So we have those nice pairs of documents that are about the same topic. We also asked LDC to produce clusters of documents. So clusters of documents include articles that are related to each other according to some query or some topic. We also got from LDC queries and their translation. So you realize that to do, for example, cross-language ARIA and cross-language summarization, you have this concept of a query. And we were able to get a large number of queries and their translations. Translations meaning both manual translations, which were built by team members, and also automatic translations, which were derived by a machine translation system that was also developed by some of our team members. Okay, for evaluation, we try to focus on two aspects. One is agreement between humans. So how do you know that you have a well-founded problem? If humans don't agree on a certain task, does that mean that you can actually produce a system that does the same task, or can you not? And we also looked at evaluating automatic summaries. Again, automatical evaluation of automatic summaries. Okay, so before the beginning of the workshop, we set ourselves three major technical goals. The first goal was to develop a summarization toolkit that will be given away to the community at large. And that toolkit would include a state-of-the-art summarizer, which deals with both single and multi-document summaries, with generic and query-based summaries, as well as two different languages. The second technical objective is to produce a summarization evaluation toolkit. Now, suppose you have your own summarizer or the one that we provide. How do you compare those two? How do you compare any two summarizers? How do you compare the summaries that they produce with manual summaries? And the third goal is to produce a very detailed, annotated corpus for further research and summarization. Okay, by putting those goals in front of us, we're actually trying to address 5 different scenarios of users who would potentially find the system useful. Suppose we have a summarizer and we want to figure out how good it is. Well, we have something for you. We can actually provide you the tools that will compare your summarizer against benchmarks and against other summarizers. Another scenario is to build a summarizer from scratch. Suppose you want to start a new research group at your university or your company and you don't have any expertise in text summarization. We'll provide the framework for you to build your own summarizer using the API that we have provided. Suppose you want to test a summarization feature. For example, does co-reference help in producing multi-document summaries, for example? Or does a better machine translation help you do better cross-lingual summaries? Well, we also have something for you. You can actually incorporate your features into our summarizer with very little training, and then run the new system as a combined whole. You can also test a new evaluation metric. One of the things that we're providing is a way to compare different metrics for evaluating summaries. And if you have your own metric, there is a framework in which you can produce evaluations of different summaries using your metric and then see how your metric fares in a meta-evaluation against the other metrics. And the fifth type of scenario that we are dealing with is when you have some sort of machine translation system and you want to either translate documents automatically and then use summarization to evaluate the quality of the translation, or to translate queries and see how that affects cross-lingual summarization of information retrieval. Okay, so the resources that we built through the last, I would say, 8 to 9 months with a lot of help from the outside and our knowledge, pretty much everybody that I could remember again. So we have the following list of resources. So in addition to the bilingual corpus, which is again English and Chinese, 18,000 pairs of documents that comes actually from the Hong Kong government news agency, we also got manual summaries, both extracts and abstracts from LDC. We got baseline summaries produced by our summarizers using default parameters, for example, random and lead-based and so on. We also got manual and automatic relevance judgments. So one of the things that we use in our evaluation is how well a summary preserves relevance in an IR system. So for this, we needed to have relevance judgments at the level of documents. And this was again provided by the LDC. The next thing that we did was to produce a very thoroughly annotated version of the corpus in both English and Chinese for cross-reference. Cross-reference is going to have the different named entities in different documents or different sentences that refer together to the same entity. For example, His Majesty versus the King of Sweden and so on. We also lemmatized the corpus and started speech tagging with publicly available tools. We also provided manual and automatic query translations, again manual from LDC, automatic manual from our team members, and automatic from the machine translation system at the Chinese University of Hong Kong. We also provided automatic sentence segmentation of the corpus, sentence alignments across bilingual documents, XML DTDs for all the major document types that are used in the pipeline, along with the converters that take the Hong Kong news corpus and any other news corpus into those formats. LDC provided us with a lot of judgments, but we couldn't get enough funding to get everything that we wanted from them. So we actually got some people at Michigan to do subsumption judgments. So subsumption judgments are between two documents and decide whether a certain document contains information that is also contained in the other document. And then if you do a summary of both, you would rather not include the repeated information. And then we also included guidelines for judges. How do you actually do relevance annotations for sentences, for documents? How do you build summarizers? One of the things that I wanted to get out of this talk is that the toolkit will be available to the community at large. And it will be very easy in relative and absolute terms to build your own summarizer using our toolkit. And to this end, we're going to provide very extensive documentation, but we already have the framework and the most simple readmes and files that you want to start. We also provide evaluation software. I'll get into a lot of detail on this a little bit later. And finally, this is bundled into a modular, trainable summarizer.
These resources do not exist in May, and they exist now.
I don't want to go through the whole list. Pretty much all of them did not exist at the beginning. In the tools, for example, the private speech taggers and so on existed, but not the versions of the tools. Okay, so the participants, we have 9 people on our team. Sanjeev already introduced them, but I want to make sure that you see their names again, and then put their names with their faces. So I have to acknowledge them at the end again, but those people were absolutely committed to this. And I was most impressed because of my prior experience at least with the way that undergraduates did. I mean, I had the idea that most of the research would be done by the senior people and undergraduates would be helping with like printing jobs and doing things like that. No, that's not going to happen. Actually, the undergraduates probably carried the bulk of the work, and I was very, very pleased to see that. Okay, so one thing I want to mention here is that the LDC was very, very crucial here. So we had several people at LDC annotate a lot of data for us. Again, sentence relevant judgments, document relevant judgments, creation of queries and clusters and manual summaries. Without this, we couldn't have done. Okay, so then the next thing is the actual talk. So this was the introduction, as you could imagine. The way that we have structured the rest of the talk is in roughly 4 pieces. And pretty much one of the 4 senior people will be giving each of those parts. But we also made sure that all of our students actually participate in the presentation by talking about some of the pieces of the work that they did. So I will apologize ahead of time for the constant switching of speakers here, but I think that you understand that this is actually a very good idea. So the next part of the talk will be given by Wailam.
Good morning, everybody. I will briefly present the IR architecture used in our project. For an IR engine, suppose we have a query, the retrieval module in the IR engine can produce a ranked list of documents. In order to do this, the IR engine needs to index the documents and produce the document representation by the indexing module. This is a typical IR architecture. The interesting feature in our project is that we also have summaries in addition to documents. So we make use of the same IR engine to index the summary. And given a query, we can also produce a ranked list of summaries in addition to documents. Normally, the query and the documents or summary are in the same language, that is monolingual IR. And in our project, we also investigate cross-lingual IR, where the query is in English and the documents or summaries they are in Chinese. So it will return a Chinese documents or Chinese summaries. In order to achieve a cross-lingual IR, we make use of a bilingual IR engine based on SMART. SMART is an IR engine originally developed at Cornell University, and we extend SMART a little bit so that it can handle both Chinese and English documents. And to do cross-lingual retrieval, we also make use of facial translation module and term ambiguation module developed by ourselves. For facial translation, so given an English query, we try to translate it into Chinese query and then feed into the IR engine. The translation process begins for each sentence, and first we try to detect phrases in the query as far as possible. In order to detect phrases, we construct a combined facial and a word English to Chinese lexicon, and we make use of the maximum matching algorithm to try to pick up the phrases in the query. So after we have detected phrases in the query, we attempt to do translation, and we look up the bilingual lexicon, and normally it is associated with a number of possible Chinese translations. Typically, it can range from 2 to 15, 20. So the next problem is how can we select one or a few good translations? This is the problem of term disambiguation. The idea is that we make use of a cohesion model and corpus statistics to help us to select the appropriate translations. So we look at the neighboring context. For example, we try to translate an English phrase or term. We look at the neighboring translation as well. And we try to make use of co-occurrence statistics in the corpus and select a different and consider different combination of the Chinese translation and select those combinations that can give us the highest score.
Are you suggesting that successive words in the sentence translate into the same word in the other language?
No. Here the problem is how to select Chinese translation for each English phrases.
What is the meaning of the line that connects CI minus 1 to CI 2?
This combination of Chinese translation gives us a good translation. So we select, so in this particular example, we select CI minus 1 and CI 2 and CI plus 1 to output for the translation.
CI2 is chosen because it co-occurs in Chinese documents with CI minus 1 and CI plus 1.
Yeah, exactly.
And so it would be unlikely for them to accidentally co-occur unless they were related translations.
Yeah, and this is what we call cohesion model. Here is some of the sample query encoded in XML format. We have some English query and a Chinese query. And this is the sample retrieval result for our IR engine. The top part is the result for full-length documents, and the bottom part is the result for the summary. So our engine can produce, can return documents or return summaries as the output. And the results are in rank list sorted by degree of relevance. Next, Simon will talk about the system architecture in general.
I'll be talking about the different evaluation measures that we use in this project. Actually, evaluation is very important. So this is evaluation of summaries. And I will show the experimental setup and how we get those measurements. So in the beginning, we start out with one query and with our corpus, which is a set of 80,000 documents. We feed that into an information retrieval engine, as Zai just explained. And what we get out is a ranked document list, ranked by the information retrieval system by relevance. Now we can calculate we evaluate the quality of this list, as in how much does this agree with human judgment. We can do so because the LDC asked one judge to provide the ideal ranked document list. So we know which of those documents are ideal. That allows us to calculate precision and recall and similar IR measures. But we can do more because one of the ideas is to summarize the corpus, the whole corpus, and then index that corpus and give it to the IR engine. This is kind of a new idea. What we get now is not just one ranked document list, maybe the one of the full corpus, but we now get the ranked document list that represents the extracts that the summarizer produced. And both of those we can provide the normal IR evaluation, but we can compare those two lists. So once we know how good the ranked list for the full document is, we're interested in how much does it correlate with each of the different summarizers that we use. So this is a loop where we have different summarizers. And we do something similar to baselines, so we compare it against random, and we also compare it against lead summaries. But the second, so the first task that the LDC judges perform is to rank documents by their relevance. But for a set of 10 documents, they actually produce extracts for us. They judge within those 10 documents that are relevant for the query, which sentences within those documents are most important. So we have manual ideal extracts. For those extracts, we cannot provide the IR evaluation. That is, there's no line going back into the IR engine because the extract we have for 400 documents, not for all 18,000. But instead, we can compare these extracts, which are manual extracts, with the automatic extracts that our summarizers produce and with the baseline summary. And this is the third evaluation that we compare the rank correlation against. And we propose to do it two ways. First of all, by co-selection of sentences. So this is looking at sentences as full entities and just counting how many sentences are selected both in the ideal extract and in the automatic extract. And the second measure actually looks into the sentences themselves and looks at how different is the automatic extract to the human extract by looking at measures like are similar words used, so we use word overlap and cosine similarity between those extracts and longest common subsequence. Because the LDC doesn't just give us the document relevant, sentence relevant for one judge, but for 3 judges instead. Another thing that we can do, and it's actually quite important to do that, is to measure a unit agreement between the human extracts, how much the unit agreement. So what I talked about was just one slice through the whole experimental setup. I just talked about English side, and I talked about single document summarization. For multi-document situation, things are changed a bit. Instead of the input being each single document of the whole corpus, we now have 40 document clusters, 40 document clusters. And each of those clusters contains 10 documents talking about the same topic. And out of those 40, the LDC have given us 20 so far. So we use those 20 for training, and there are other 20s that are yet unassigned. So each of those clusters gets summarized by extraction, both by the LDC judges, as well as by our automatic summarizers, as well as by the 2 different baselines. And now, those extracts can be compared just in the same way as we compared the single document extracts by the same method of summary comparison. But the new thing here is that the LDC actually provides us with manual summaries. So in contrast to the extracts, these are summaries that are actually written by the judges from scratch. And this is something that is very important in the summarization field and hasn't been compared in such a large scale evaluation before, which is how do people differ in the task of writing summary from scratch to extract. For this one, we actually cannot use summary comparison measure 1 because that only works when the sentences that are produced in the summary are really the same sentences. But what we can use are those more content-based similarity measures. So I'm handing over to you. value.
Okay, so as Simona said, the LBC provided us with 40 clusters, and each of the clusters has a topic associated with it. You know the documents in it, that kind of them are related to that topic. Here I'm showing you the 20 topics that we have had access to during the workshop. We split them into two parts, 10 for training and 10 for dev test, so that we could actually give you results today. And we also have 20 more queries coming in the future, which will be used, well, once we fully train our system on both training and dev test, we'll be able to do a separate testing on those 20 new queries. So you can see that there's a wide variety of topics, and that the query topics are very short. They're very different from thread queries where you have also narratives and descriptions. And by the way, this is what we actually translated into Chinese, both manually and automatically. Okay, so now, the kind of annotation that we did included what I said earlier, the different part-of-speech type versions, XML, and so on. But what is really most interesting, I guess, is the kind of summaries that we produced and the way that we compare those. So the first group of summaries is based on the full set of 18,000 documents. So we had a total of 135 errors from the 18,000 documents. So if you multiply the two, you get the total number of single document summaries that we produce using different compression rates, different summarizers, different languages. We have a total of 10 compression rates from 10 to 90% and also 5%. We also have word and sentence-based compression. So in one case, we measure, let's say, 10% of the original document in sentences or in words. And it turns out that those are significantly different. We also have again English, Chinese, and cross-lingual retrievals, not summaries. So once we get the English documents and the English summaries, we also get the Chinese documents and the Chinese summaries. Then we run both sets through the information retrieval engine, and we get the ranked lists of full documents, ranked lists of summaries in both languages. But we do this in a third setup condition where we actually have a query in English, which is translated automatically into a Chinese query, and then we retrieve the documents in Chinese. So that's why we have those things. And we have 10 summarization methods, meaning 10 different summarizers, which include the two baselines, 4 versions of the summarizer that we built here, and the rest are summarizers that we use from other people outside this workshop. We also got manual extracts, which we can use to compare with each other and with the automatic extract. We have a total of 80 runs on 200 documents each. 200 documents again are the 20 queries from training and dev test, and times 10 documents in each. We again have the same 10 compression rates. We have this word sentence distinction, and we also ask 3 different judges to perform this task for us. So we have actually output from 3 different judges plus the average judgments of the 3 judges. So that's in a sense, it's 4 different judges. As far as the multi-document summaries are concerned, we again have manual and automatic summaries. The multi-document summaries are, human summaries are 3 lengths. Those lengths were chosen to coincide with the length that we used in the doc evaluation recently, 50, 100, and 200 words. We didn't do 400 words because our documents were on average a little bit shorter than the doc documents. We had again 3 judges produce those are from LBC. On 40 queries, so far we have received 14 of them. This is a task that was added to their to-do list late in the workshop, actually the 2nd or 3rd week, and they're still working on them, but we're perfectly pleased with the fact we were able to get 14 to do the evaluation so far. Okay, so multi-document extract. So the difference here is that the summaries are abstract. Those are written from scratch by the humans, and that's one of our most important comparison points. Whereas the extracts are, again, sentence-based. We have 2 types of those. We have automatic extracts. We have a total of 160 of those. Again, with 8 compression rates, 5 to 40%. We restrict ourselves to the shorter versions, not 50 to 90. Plus the 50 to 200 absolute word compression rates. We use those 5 to 40% to compare with the automatic ones, and we use the 50 to 200 to compare with the manual sums. And we have this with 20 clusters right now. The second part is 320 manual extracts. Okay, so those are again produced by the LBC at 8 different compression rates, times 10 clusters, so again the same compression rate, 10 clusters. Again, we have P judges and average of all judges. Okay, so the next part here is from our lecture.
Good morning, ladies and gentlemen. As Drago said, we have several kinds of summarizers here. We have meat, websum, summaries from GUE, and also lexical chains, and also align-based summarizers. I don't explain alignment because then you will explain the alignment summarizers. So, and also we use this summarizer on English documents and also Chinese documents. And we get also single document summaries and also multiple document summaries. For example, we use websum and we get multiple document summaries. Here are some examples from different summarizers. As you can see, you can see some similarities between summaries. For example, lead and random, and also from me, so in first emphasis. Here is the Chinese summary, so if you can read. Did you see the similarities? These are our big chart that shows what we have about the tables. So the cross parties are the first time queries, that the training queries. The stars and states are the first time queries, and also plus the other time queries, the next time queries, that these are the dev test queries. So as you can see, we have English summarizers here, up here. In the middle is Chinese retrievals, Chinese retrievals here. We have also crossing retrievals. As you can see, there are some different meat versions here. For example, the meat orange are the first original meat that works with default parameters. And also, for example, the meat 002 or meat 2, for example, it uses the position vector and cosine similarity with title, and also centroid property. So, and also there is another thing here is that there is also another meat that works with parameters that's coming from the supported vector machines, like trainable meat. And so we have more than 10,000 vectors, and they are coming more and more every day. So that's it.
The translation, you have documents in English and Chinese.
Sorry.
You have documents in both English and Chinese. Are these sentence-by-sentence translations for these normal translations in which the translator?
I don't know. I don't know.
Let me answer this question. The documents between the single and LDC are document aligned. So we know which document in one language corresponds to the other. They're not sentence aligned. We did the sentence alignment ourselves, and Daniel will talk about it.
So I'm going to talk a little about one of our summarizers, Mead, which I worked on throughout the workshop. And this summarizer is actually technical objective number 1, the deliverable stage, the trainable summarizer. And along with Elliot Drawbeck, I helped to re-engineer the summarizer and modularize it. So the way this is going to work is I'm going to talk a little about the algorithm, and then Elliot's going to talk about the new architecture that we designed. So Mead is an extractive summarizer, and that really just means that the summaries that Mead produces have sentences which are identical to the sentences in the original document. So extractive summarization can be viewed as a classification task where a summarizer is just a function from
subsets of sentences in the original document into 0-1 judgments. So is this subset of sentences a valid summary? But of course, this raises a large combinatorial problem. And Mead, and in fact a lot of other summarizers, handle this problem by classifying individual sentences as in or out of summaries. Mead's classification function first is based on a score there's a linear combination of the features that sentences have. So when Mead goes to classify a sentence as in or out of a summary, it first calculates a score for the position of the sentence in the document. So the first sentence in the document gets a very high position score, the last sentence gets a very low position score. Mead's centroid feature is the similarity with a vector-based representation of the salient concepts in a document or a cluster. And the first sentence similarity, actually, this turns out to be very nice for us because our first sentences are really the titles of the news articles. So this is really similarity with the title. So what we do is we measure this sentence's similarity with the title in hopes that the words in the title also are a good indicator of what's salient about a document. So eventually, once we get these scores, which are weighted by these weights, so W sub P is the amount we weight the position, we end up with an ordered list of sentences. And then classifying a sentence as in or out of a document is really simple. We just choose the sentences with the highest score. But unfortunately, Mead, in any sentence that treats, in any summarizer that treats sentences on an individual basis, runs into the problem of redundancy. So these are actually two sentences from the first document in the cluster, and you can see that they repeat some information. If you were writing a summary, you probably wouldn't want to put both of these sentences in. On the other hand, if you're classifying sentences on an individual basis, they both seem to represent the salient concepts about the document. So Mead actually has a method for combating redundancy, and this is especially helpful when you are summarizing multiple documents in a cluster that are in general about the same topic. So what we begin with the ordered list of sentences that I talked about in the last slide, and we begin by adding the sentence with the highest score to the summary. And then we add the sentences with successively lower scores, but before we add them, we first make sure that they aren't too similar to the sentences we already have in the summary. So we end up skipping the sentences that are too similar and moving on to the next ones. So this method for combating redundancy is a little naive, and in fact, in the future work section, I'm going to talk about more sophisticated measures. But it, along with the linear combination of features, provided a sort of a first step for Elliot and me when we went to design the new architecture, and we wanted to make both of these sort of more extensible and modularize them. So with that in mind, I'm going to turn it over to Elliot, and he's going to talk about what we did.
All right, so the two main distinguishing features of the two main modules are the one that classifies individual sentences on an individual basis, and then the one that sort of massages those individual sentence evaluations into a globally optimal set. So we decided to modularize with that in mind, wanting people to be able to really quickly take those particular modules out and plug something else in without having to rework the entire architecture. We split the classification of individual sentences in two parts, where Mead works with the centroid score, similarity with first sentence, and position score in one field to substitute in arbitrary descriptions and features about each sentence. We want to use where
Mead uses a linear combination of features. We wanted to use some more sophisticated technologies that are available. And the re-ranker, massaging things into the more globally optimal extracts is probably the part that is most open-ended. So that maybe one of the more difficult modules to work with, but it's also one of the more interesting ones. So that's completely general, whatever you want to do with that. We think that we have already put modules that we've plugged in, included some more advanced features. We've had to look at query-based features. Did some very simple things with how many words in the feature are also in each sentence. We use vector machines and maximum entry models for classification. And we'd like to do a lot more things. We started working with named entities and just look at a sentence, does it contain a named entity, or what kind of named entity does it contain? It's a good indication. And try to do something more semantically motivated as far as similarity to the query. And like I said, the re-ranking algorithms are pretty open-ended, a pretty open research question of what is useful to do there. One particularly exciting thing, though, that several people are interested in, is trying to get a machine learning algorithm to approximate some judgment of which sentences are similar, are meaningfully similar to each other, or semantically subsume one another, or have any manner of relationship between them. John's going to be working with that.
Good morning, everyone. I will introduce the sentence alignment system we used in the workshop. The basic algorithm we use here is borrowed from GTGL. The original algorithm we know is based on English to French and German, but now we adapt this algorithm to Chinese, to English, Hong Kong covers. The major difference between these two systems is the length. Basically, it's the length rate between two languages, English, Chinese, English, French. Okay. So first we need to make sure basic assumptions. The fact that longer sentence in one language can translate to a longer sentence. The same, the shorter sentence should be translated to the corresponding shorter sentence in another language. And adapt to English, Chinese bilingual corpus, we compute the length rate between English and Chinese character. We get the parameter here is the mean value is 0.65. That means each Chinese character generated by each English character, the length rate is 0.65. Okay, this is the evaluation. The evaluation, after we re-implemented the sentence alignment system, we manually get some result and then evaluate the current system. We randomly select 20 document pairs, which contain 200 sentence pairs. Then we get the result of this. Okay, let's see, the 16 document pairs, the precision is 100%. And one document pair is precision is 95%. And 3 is 77%. So the average precision is 95%, quite high. So because the manually check is time consuming, and so now we only select randomly 25 document pairs.
Okay. Get back to the question you asked before. So the number of sentences are different from the two documents, right? Otherwise it would be tricky. And
yes.
How do you judge that the alignment is correct? So that means if you're aligning are you allowed to align one sentence to two sentences, or are you skipping? That's fine. That's this one. Okay.
Yes. Okay. So first we got the flat file, English and Chinese. Okay. Then we use sentence segmenter. Segment the Chinese file to Chinese docsend, and English file to English docsend. Okay. Then we got the original alignment. Okay. 1, 1. Then we manually check 1. Then compare with the line for system. Currently, we only consider 8 cases. That means zero English sentence match one Chinese sentence. The difficult part is 2 English sentence match 2 Chinese sentence. Okay, so first we got a manual result. Then we got compare with the system output. And this one is a statistical method and the content result. The total number of sentences here is the number. You will see if you add the second column total together, the result is different from total. The reason is in the pair 2 match 2, we added 4, multiplied by 4. Okay, so the precision and record is here. This manually check result. So currently the sentence alignment evaluation is independent package. If you can give me a sentence alignment based on English to Chinese, I can test your system. Okay, thank you.
Do you know the repeatability of the human results?
Pardon?
The manual alignments.
Yes.
Do judges agree? So you don't know whether judges agree?
Yeah, I judge myself. because the judges have to learn something in Chinese. Okay.
So I'll be talking about the review agreement and different measurements, how we measure how much use we on experts. And my part of the presentation is 3 measures that deal with co-selection. So this is only comparing extracts with other human extracts. And first of all, I have to mention that the form in which we get the judgments from LBC is not in binary form, so we don't get different extracts with different compression rates, but we compile those because we ask judges to judge for each sentence how relevant they find it on a scale from 10 to 1, 10 being the most relevant sentence. That gives us the ordering of the sentences, and then we can produce extracts of different lengths. And I'll start with the first measurement, which is percent agreement. That's kind of the simplest measurement of the thing. And so if you have a contingency table of what 2 judges think which sentences, how many sentences are relevant or irrelevant, this cell A here mentions all sentences that are thought relevant by both judges. And this cell D mentions all sentences that were thought irrelevant by both judges. And percent agreement between 2 judges is simply the sum of those 2 over all sentences that we see. And we do this pairwise for each of the 3 judge-judge pairs. And I've plotted this against the compression rate. So we have 5 to 9. What happens here is that agreement seems to be very high at the very short summaries. And again, it seems to be very high at the long summaries, 90%, where basically judges only have to decide which 10% of the sentences we omit. And here, in the middle, around compressions of 50, percentage agreement is much lower. And we were wondering why this is the case. So this is, by the way, this data is compiled over 200 documents, 20 plus years. And there's a problem with this evaluation method, yes?
But if you imagine what is the worst possible score, if you're selecting 90% of the sentences, so you only leave out 10, the worst possible score is 80%, right?
Yep. And a random score was
Exactly. I'm getting to this. Actually, I'm critiquing this evaluation method. That is still used a lot by people who measure case value. So this is exactly the point. What this method does is overestimate here, for example, it overestimates the contribution that the irrelevant sentences do. What we're really interested in is, especially in these low compression rates, what are the sentences that judges agree on and that still surprises us? So yes, ma'am.
And also, this particular measure is not affected by
individual judges. So one judge puts all sentences in the range 6 to 10, and the other judge puts everything in the range 1 to 5. It still would affect you because then at 10% you take the top 10% of Judge A and the top 10.
It's a partial order, yes, we take
So
whatever.
it wouldn't matter. So if I'm a very biased judge and I give a very unfair judge, I can lose to a 20, it won't matter because we'll still take the top
Because we
10.
take half.
But still, according to this measure, the agreement between the judges is about the same as if they pick sentences randomly.
Well, it's higher, but you
I don't
also
show
can
that.
find how to compare them around.
I don't show random. I show random against the better measurement. Actually, we're not really considering this as a serious measure. I'm just trying to develop which metrics we use. So, as in IR, where there's a big where the distribution between relevant and irrelevant items is very skewed, we decided to use as another measure precision and recall. Now, precision and recall only looks at the relevant sentences in contrast to everything else. So in this case, it really only takes A as a measurement. And A in this case are, again, sentences which are relevant by both judges. Compares them either against A plus C or against A plus B. And if you notice here, the position of one judge, we're comparing two judges. The overall measure gives the average overall judge. The position of one judge is the same formula as the recall of the other judge. And also, because in the experiments that I'm recalling on, the judges always chose the same number of sentences, so we actually know that position and recall is the same number. I'll just be reporting one single number, but you should keep in mind that it's position and recall. So on this one, I've actually plotted the random one. The red line shows us how much human judges agree if you measure it by position and recall. So we actually see that random is quite high. And it's increasing with compassion. But this is also not what we want. We're really interested in a measure that gives us the agreement after you subtract it random. So it really gives us agreement that we're interested in. But just, okay, I put this other slide, which actually shows that even though it has this problem with random, this measurement is quite robust across clusters. So there are some clusters in which all across the compression range, position and recall is higher than others. And I'll come to this difference amongst clusters when I introduce the last evaluation that we use. And that one is kappa. The formula of kappa calculates agreement, and this is the actual formula by which it's done. It's basically calculating out of how many agreements there could have possibly been, how many are there. But then kappa subtracts the random expected error. And the way how it calculates the random expected error is by the distribution, the observed distribution of the categories. And this is what this formula will tell us. So one nice feature of kappa is that no matter how many annotators you have, how many categories you compare against, and how the distribution of the categories is, it always gives you a numerical value that is comparable to each other. But because we're looking at the actual real agreement that is different from random, we get numbers that look much lower than precision recall and percentage agreement. So here, if we average over those 20 clusters, again we have some highest values that are just under 0.4.
There's something that tells me what 3-4 slides back, when you had the precision and recall together versus random.
Would you like me to do that?
Yeah, go back to the 24 slides. Yeah, right. So the kind of compression that I would want to be looking at 10 and 20%, because I'm like, and is this saying that if there was a 100-sentence document and you were asked to pick the 10 most salient, and I was asked to pick the 10 most salient, we're now talking 10% compression, then we would agree on only about 2 or 3 of those sentences?
Yes, yeah, that's the case. That is actually the case when we look at the data. It's actually well known from the literature that people don't agree much or this is what's always been claimed, but people usually measure this in precision recall or in percentage. And I think the kappa is actually very much. Well, we didn't expect agreement of kappa in the 80s or something like this. But we didn't really get one. Is there a question?
Right, is that because each sentence was squared, and not every human just made the sentence?
It might be the case that there is an effect that we might have gotten slightly different results if we had actually asked our judges, okay, please give us an extract of 10 sentences, please give us an extract of 10 sentences. But we're quite confident that the way how we asked them, which is by the scale between 1 and 10, it saves us a lot of time, as Gago will be talking about, it has some other advantages. And I think it actually can be translated very accurately into those extracts.
But it also has a problem, right? The redundancy problem, you know?
Yes.
I mean, because
We'll
talk about that later.
This is actually easier then, because if you have two, let's say you have two sentences with very high score, if you force them to pick the best sentence, then they'll pick randomly, and so you get a 50% accuracy. And so it looks like they're not agreeing. In this case, you're saying, okay, you can pick them both, and you'll agree. At the point where you pick two of them, they should agree. Even though if they had to pick the best 20 sentences, they would always leave out one of those best sentences, so you never get agreement. So this measure says that is a much more easy test than seeing whether when you make a 50-sentence summary, they agree. And so I'm still disturbed that given this much easier test than comparing actual extracts, their agreement is barely better than if they had just thrown darts at and to pick the order.
No, but according to your argument, isn't it the other way around that if we, as Drago will do, if we had compared directly the normal scales, then it should show that both judges have given a 10 to one particular sentence. But hereby, we're just having cutoff points at 5%, 10%, 20%. Extra sentence would actually get into the measure.
this is just okay, here's how it works. You have the absolute values with sentence, and you produce 5% extract, 10% extract.
Right, so it doesn't matter what scores they get.
Yeah, this is not yet. This evaluation here just looks at yes or no, still binary. The next evaluation after kappa will look at the actual absolute values.
I thought this said, given that they rank all the sentences, each judge ranks all the sentences within a story. They do it by giving scores, but effectively it just becomes a rank. So now you
then we
say...
pick the highest. We
And then
don't
you
pick
say-
a certain cutoff, but we just pick the highest. If one sentence
Right,
decides
so
to
now
give
you
you
say...
6,
Right, so
that's the
now you say,
highest.
I want the 10 best sentences from each judge for this story. Okay? So there's no issue about what score they give.
Not yet.
The 10 best.
Okay.
And I'm saying this is an easier test than asking them to make a 10-sentence summary. Because if they made a 10-sentence summary, they would each, I'm presuming that there are two sentences that are both very good, and they would each leave out one of them, a different one, probably. Whereas here, when you pick 10 sentences, they should both include both of those sentences. So you don't have the problem you would have if you compared real extracts. Okay, so again, at the point where you say pick the best 50%, you would expect that the top 30% of those would be in 100% agreement, and it's only the last few that the rankings would differ. While this is getting about the same performance as if the ranks were completely randomized numbers.
No. We're not getting yet to the evaluation where we look at the actual score. This is still yes in the summary, no, not in the summary. We get binary judgments from both judges. So
I get
the
it.
point is very good, but we're not there yet in the presentation. We'll just wait another 15 minutes. Yes.
Are the judges told not to bias themselves about redundancy? So
We'd ask them for redundancy in a separate evaluation. That's the subsumption evaluation. We'll also talk about it later.
Those judges were not told anything about redundancy at all. They were asked,
so
judge,
did you
give
guard against it? I mean, the tendency might be, well, I like that sentence. this sentence is very similar, and I'd like it if I didn't see the first one, but I was going to rank it very low.
It's actually a complete experiment would actually do both of those things together. But traditionally, we could only ask them for one of the judgments, and we asked them for individual redundancy, individual relevance, not looking at redundancy.
So you don't know how...
We don't know that because it wasn't done in the same experiment. But what we've seen from the literature is actually that agreement, as I showed later on here in Kappa, it's not unusual to be like that. People find it very hard to agree. So, papers from 60 onwards have reported something like 50%, but that's percentage agreement. So actually, Kappa is a much stricter measure. So what this shows is Kappa at different compression rates. And overall, we've seen from the average on the last slide that Kappa grows with compression rates. And here in this case, for example, there are some perfect agreement cases, but they only appeared in the higher compression. So here people were quite, they were agreeing on which sentences to throw out. But another reason why I showed this particular graph is it shows the large variation across clusters. And when we gave our judges the task to select a cluster, we didn't really say on the basis of which, we said the same topic. But they chose the clusters on the basis of, and the queries on the basis of very different criteria. I think this is one of the reasons why we see such a large variation across clusters. Here is, I've just taken one slice out of here, which is human agreement at 40%. And we see that for some of the clusters, we have Kappas that are actually quite high, considering that, we didn't train those annotators, didn't feedback on them. This was, they were completely independent of one another. This was a one-time task and got back our results. For other clusters, and you'll see in the other evaluation measures that something similar happens actually in some of the same clusters. Here, cluster 551, talking about natural disasters, that the agreement is actually very low. People didn't agree. So, one last thing that I'm showing here is Kappa for each of the clusters, but instead of just showing human agreement, we've done the following. We have this annotated pool of 3 judges, and now we put one system into the annotated pool at the time. And the reasoning is, if this was another human, we would expect the kappa value to actually stay the same. Because it's a machine, we expect kappa to go down. And now we measure how much it goes down. Kappa has the nice property that if you measure random between one random process and another, as a human, for example, kappa is 0, and we actually found that experimentally. Here, something similar is happening. We have 3 judges plus a random process, and kappa goes down a bit. It doesn't go completely to 0. And we see that if you compare several summarizers against it, they perform under human performance. Now, if we put, actually, I think it shows better on the next slide. These are 3 humans agreeing. If we put a lead summary, which is the first sentences, into the human annotator pool, agreement actually increases a bit. And this, the only explanation for this is that the aspect in which humans agreed most was the leading sentences, must have been the leading sentences. But putting the leading sentences in actually reinforces it again. And you see that random here is just under 0.1. Those previous results were on single documents. For multi-documents, we actually have manual extracts for the first 10 clusters. So these are the results, and actually they are, each of those points now doesn't represent 10 documents that are summarized, but it's one summary, one extract for each of the documents. And we see if we compare meat against the humans again, we see that it's kind of a similar picture than in the one before, except that here agreement is higher in this document. So that was my last slide.
So this is saying if you have a particular human judge and you compare him with another human judge, you get some agreement, some disagreement. If you, and your score is by measuring how well you compare with the other human judges. If you were now appointed another judge, and you were told you're going to be scored as to how well you agree with all of the judges, rather than doing your best job of summarizing, you would do best at that task by just picking the early stories. Is that what this is saying?
Yes, that's what the previous slide
Just pick them in order that they come.
That's what the previous slide is saying. The single aspect that we can identify, that we can isolate from where the agreement amongst the humans comes from, seems to be the leading.
But it's not only that it's a single aspect, it's that if you blindly pick sentences just based on an order, you will agree with the three judges better than if you do your best job of picking scoring sentences by any other means.
That's what this is.
By any means available to you as a human.
Would it be a reasonable interpretation of the results that you presented to say that co-selection of sentences carries little signal in terms of evaluating the quality of summaries?
And this is why one of the next measurements that actually goes into the content of the summary. This has been suspected for long, co-selection is just one thing. Actually, overall, it's quite, a negative.
You said that you add to the human judge when you go meet, and you get the new number. Will that throw you in another pool where you're thinking about something? Basically, will you take it to the 30% because you added some stuff?
Could you repeat the question?
The fact that you added some sentences to the human 20%, will that put you in a 30% then? Or is it the same then?
I didn't add any sentences in. What Kappa can do is compare more than two annotators.
No, you said the lead column, right?
Yes.
It's changed by adding to the human judgment.
What this column is agreement between four judges. Three of them are the humans, that's my human annotator. And then I add in a completely different opinion, which in this case is the lead. All of those, so this is comparing between four summaries, each of which are 20% long. And that was my last slide. Okay, the message also here is that multi-document kappas are higher than what we've seen so far in single document. And this might be a side effect of how we ask judges to make these judgments.
To the comment here. Simone started with the post-election evaluation metrics. And we're going to add 3 more categories of metrics. That's what Horacio and I are going to talk about later. Each of those different types of evaluation metrics adds something that post-election does not count. So there are also things about redundancy, different compression rates, and so on, which will be at least partially solved when we introduce those new metrics.
Good morning. So I will be talking about content-based evaluations. So basically, you take two texts and you have a function that measures the similarity between two texts. And you take a number between 0 and 1, 1 meaning that the texts are highly similar. So if we take, for example, precision and recall, and we take as text representations the numbers of sentences that are in those texts, you only take the index of the sentences and you have these two sets. This set is the ideal abstract, and this set is the extract produced by another human or by another system. And these indexes are not the same, they obtain 0, meaning, well, your system failed in this particular abstract, in producing this particular abstract. But what happened in sentence 1 is the US president visited China, and sentence 4 is the visit of the president to China. So we have the very same content. So we would like to use more content-based measures to evaluate how good or how bad summaries are when compared with ideal summaries. And the idea here is to use vocabulary overlap, and there are many similarity measures for vocabulary overlap. And you can think, instead of thinking about indexes of the sentences as a representation, you can think about more richer representations. You can think about bags of words, for example, or bags of different types of tokens. You can think about sequences where the order of the tokens are important, and you can also think about text in a vector space where tokens have some relative importance in the document and within the whole collection. And the units that you can use to represent your text can be words, lemmas, and phrases, and of course you can have different categories like verb, nouns. If you think that nouns carry the essential meaning of the text, that you can decide to use, for example, nouns to measure the similarity between text. So I will present two frameworks for evaluation. So the first framework is monolingual evaluation in English. So we start with a full document. We have a set of full documents, and we have a set of human extracts produced by LDC. LDC produced sentence judgments, and we have a system that picks those sentence judgments and produce pseudo-human extracts. We also have in our framework multi-document summaries. These are summaries produced from scratch, so they are completely new documents, and we have automatic extracts, single and multi. So the question is how to compare all these units. So you can, as we have different extracts for the same document, we can compare among them. But we can also compare the multi-summaries among them because we have three judges producing different summaries. And you can compare human extracts with single automatic extracts. You can compare multi-document summaries with multi-document extracts, and of course you can always compare with the full document. Of course there is this problem of length of the text representation, but you can anyways apply content similarity measures to compare with the full document. What happened in the cross-lingual environment? We have Chinese text now, and we have full documents in Chinese. We have automatic extracts in Chinese, both in single and multi, but we don't have manual extracts. But we have this wonderful corpus with alignment text. So we decided to take advantage of this table of, that's myself, advantage of that table of alignment in order to produce human extracts by sentence alignment. So now we have again some kind of ideal extract for the Chinese corpus. So again we can do here compare the Chinese human extracts, the full documents with single and human extracts over. And so we can repeat everything that we have in the previous framework, but we can't repeat the manual multi-document after because we don't have that for machines. So, yeah.
In the previous slide,
Yeah.
you could compare the sentence alignment between English human extract and Chinese sentence alignment. Thus, you are relying on the assumption that the sentence alignment algorithm performs 100% perfect.
Yeah. We haven't measured any errors here. Yeah. This is very, very preliminary and came into our framework in the last 2 weeks of the workshop. But we think that it's a good starting point to evaluate the summaries in Chinese.
So actually, have you actually evaluated how well the alignment?
The alignment is evaluated only on 20. Was evaluated only on a subset of 20 documents. It's very small. And the precision is very high in those, but we need to do a better evaluation on the automatic alignment.
If I understood before, you're saying that your measure was different variations on words, the same words being used.
Yeah.
Okay. So when you're comparing an English extract with a Chinese extract, how do you measure whether it's the same word?
The error is not the same meaning. The error is here of the table of alignment that produces the human extracts. It's not the same meaning as comparing here. The error means we produce from extracts in English, we produce human extracts in Chinese, and here we have a framework for comparison. Sorry about that. Yeah, it's not the same. Okay, so talking about text representation, so we have this. We receive from LDC completely unannotated corpus, and we produce automatically, and with some manual corrections as well, a completely annotated corpus where each sentence contains information about each token, and you have syntactic information about each task and lemmas. So that gives you the opportunity to explore different text representations. So you can extract, for example, from this sentence, you can extract absolutely all the tokens, or only all the tokens but in lemma's form. And you can extract, for example, you can think about extracting all the words that are nouns, or all the words that are verbs, for example, if you're interested in measuring something, or all the lemmas that are words that are nouns. So, and this gives you different representations, and you can also think about that your tokens have some relevance as well, so you can compute their frequency and inverted document frequency and associate some weight in your representation. So these are the basic similarity measures that we use, cosine similarity between two texts. We have two options here, or we use cosine 001, in which you only, the text representation, you say this token is in the text representation or is not in the text representation, or you use some weighting scheme. We have, so here the representation is a vector. In word overlap, we measure the representation is a set, and so we work with sets and we just do intersections of vocabulary. And always the measures is going to be 0 and 1. And this is the longest common subsequence. So longest common subsequence is computed using how many deletions and insertions you have to make in order for the two strings to be similar. And this is the formula for the longest common to the string. Of course, that you can take two texts and say, well, compute now the similarity between two texts using longest common subsequence, but we decided to do different. We decided to take all the sentences in one ideal abstract, all the sentences in the automatic abstract, comparing the longest common sequences, pairwise comparison among sentences. Then we take the maximum in this side, and we sum all the maximums. We take the maximum in this side, we sum all the maximum, and then we normalize with the maximum possible that we can obtain in this way. And well, this is the example of the motivation why longest common subsequence. So you have the US President and the First Lady, and the President of the United States and the First Lady, and of course you have 1, 2, 3, 4, 5 as your longest common subsequence. Of course, that you can imagine a completely unrelated string, and you will always also can obtain number 5 as your similarity score. And sorry about the characters, we haven't loaded the. But the translation of this sentence in Chinese and the translation of this sentence in Chinese gives exactly the same string. So you have complete overlap in the case of Chinese for this particular. And well, so we can do everything in the framework proposed. So I will give some numbers. Of course, there are many dimensions because you have different text representations, different measures that you can evaluate on different text representations of. This gives you an enormous space for comparison. So here we are comparing humans against humans using a particular measure, for example, cosine using lemmas and nouns. And these are the clusters. So I only did comparisons with a limited number of clusters and limited number of compression rates because it takes too long to compute all the numbers. So, and you have different compression rates, and so this will give you a measure of how related are the extracts produced by humans. And you can, of course, put that as an upper bound for the comparison with when you're comparing extracts produced by machines. This is monolingual again with another measure, so you can explore different measures and different clusters. And you can do the same with cross-lingual. And again, you can obtain an upper bound of similarity on content based for an evaluation of automatic abstract. these are measures on the monolingual, that means in English, with one particular cluster, for example, and we consider all the summarizers that participate in our evaluation. And we are interested in seeing how this measure of cosine, how this is related, for example, with other well-known measures of similarity between extracts and human extracts. So this measure allows you to run systems. Here, for example, this system is performing better in cosine similarity than all the other systems. So it will be interesting that we will explore if this measure is related, for example, with precision and recall, for example, or with kappa or other measures. This is another system, another possible combination of features to evaluate cosine. And again, the very same system using this evaluation runs better. Here is for all the clusters and all the compressions, and in this case, these systems get the lead rate is not well. In this case, it's not evident which is the system, because sometimes you have this system here, sometimes you have other systems that perform better here, for example, here. And here you have the system. So it's not clear with this number which is the best system in this knowledge. We have a measure. And here is cross-lingual evaluation, the very same idea with a single query. And this measure allows you to decide that this system performs better in this evaluation, for example. Compression rate. But if you take another measure, you can have differences. So for example, this is for all clusters and all others, so you get this system that is performing better in more cases. And very similar performance. So multi-document summary, so you can do the same for multi-document summaries, and here, again, you can obtain an upper bound, for example, of what you can expect when you compare with multi-document summaries with multi-document extracts. So again, some of the clusters are behave differently. You can see, for example. And this is, well, the thing that we produce, the last thing that we produce is the comparison between the multi-document summaries. These are written from scratch with automatic extracts produced by only one system in our evaluation, and with manual extracts, multi-manual extracts produced from the judgments by MPC. So the measures are really very low in all the cases. But you can see that there is more agreement between, there is more similarity between summaries written from scratch and manual extracts than between summaries written, multi-summaries written from scratch than when we compare with automatic extracts. And you can see as is expected, the measure goes upper as compression increases.
Yeah, one thing that some people may not have realized is that in the summarization community, lower compression rate really means shorter sentence. So 5% means 5% of the original document, not 5% compression. Just tradition. I just want you to be aware of that. Okay, so now we go to the point where we can actually address those non-binary judgments of the judges. So on the left-hand side, I have a situation where you have an idea for one judge or for multiple judges. It doesn't really matter in this case. there is a 20% extract from the 10 sentences, and the judges have picked sentences 1 and 2. And you want to decide which one of two systems, system 1 or system 2, does better, and by how much. Well, if system 1 picks the exact same sentences as the ideal, obviously it should get the highest possible score. The question is, what do you do in the case of system 2 which only picks one of the two sentences and then picks another one? Well, we looked at two different approaches to this. One was to look at percent agreement. A percent agreement in this case would be 8 out of 10 because it would include both cases where system 2 agrees positively with the ideal summary, and also the 7 cases where it agrees negatively. Precision and recall, however, would give this 50% on both precision and recall because out of two sentences in the ideal, the system has picked one, and the two sentences picked by the system, only one is good. So how do we plug in non-binary decisions into this? Well, here's how. Suppose instead of asking judges to tell us what are the two most important sentences, we ask them to give important scores for each sentence on a scale from 0 to 10. So one possible way that we could have gotten those two classes here is, in this case, this is a real example, by the way. We have a 10 on the first sentence and an 8 on the second sentence. And then we have a bunch of lower scores. So when we want to produce a 20% summary, we would rather pick those two sentences, right? Well, but the question is, now, if I decide to pick a sentence that has a 7 instead of a 10, should I be penalized as much as if I had picked a sentence that has a 2? And I believe we should not be penalized. And we actually did a lot of experiments, which I'm going to report on in a few minutes, showing the level of inter-judge agreement using relative utility, which is this metric that was introduced last year in the paper. And then I also show you how we can use this metric to compare automatic extracts with humans and with random. So relative utility essentially says in this case that I could have gotten a maximum utility of 18 points. This is according to the ideal summary. If I pick the same two sentences, I'm going to get 18 of those points. So that's a relative utility of 1.0. Whereas if I pick this sentence here with a score of 8 and this sentence with a score of 7, that would give me 15 out of 18 points, relative utility, which is better than picking, let's say, this one and this one, which would only give me 10 out of 18. Yeah.
Where the sentence is scored independently, or considering I scored that with 10, now this one I would score it
independently. They're scored independently in this experiment. Later I have another experiment to show where we ask judges to say, if this sentence was in the summary, what would you do with this other sentence? And that we don't have full results for that part. We only have for this one.
I have a question about these numbers.
Yes.
I was thinking if I was doing the task of assigning these numbers 1 to 10, I would probably end up having, I wouldn't use all the numbers. I would probably use 9 and 10, I would probably use 5 and 6, and I would probably use 0 and 1.
Well, we actually did this experiment with several different judges, with 10 different judges and 2 different experiments, and they're not like you. We have much wider distribution. On the other hand, we do have a discrepancy. I mean, I don't have a slide that shows the distribution, but we do have a lot of 10s and 9s. Then a lot of 5 scores, 3s and 2s. Very few 1s and 0s.
Okay.
And very few 7s and 6s.
Because I was trying to think, what is a 7?
Yes. So we actually look at this. We look at the way that humans agree with each other on this one. That's the next slide. Okay, so this thing shows you on 10 randomly picked, on the 10 documents from a randomly chosen jury, which are A to J. Inter-judge agreement with relative utility. And I don't have the formula that shows you how this is computed. That was in a presentation that I did last year. But the way it works is that you look at all possible pairs of judges, and you decide you're going to place each of the judges in the pool with ideal summary. And then you want to measure how much they agree with each other. And the way it works is that you get into judge agreement that looks like this. So 0.7 on this particular document, 0.65. And so this is done at 5%. And I have similar charts for 20% and for 40%. Now, what is important also is that in relative utility, you can also determine a lower bound on your performance. And the way it works is that you specify the compression rate, and you take the average performance, the average relative utility of all possible systems that give you 2 sentences in the average, or 5 sentences, a given number of sentences. So you can see that random is relatively high, so it can be 65, it can be 45, or 6. On average, we have a number of around 0.51 on relative utility for random. On the other hand, the average agreement between judges is about 0.78. And so the question then becomes the same way as Kappa compares a system with random. Here we can do the same thing, but we can also compare with inter-judge agreement. So in a sense, we have a lower bound that is random performance, and an upper bound, which is inter-judge agreement. And then this gap here between one and the other is where most summarization systems should fall. Now you can see that this gap is pretty consistent across compression rates, so 5%, 20%, 40%. We still have large gaps which are on average about 15%. So going, for example, for this compression, I don't know the exact number of the graph, from 65 to 0.8. Okay, so now, the next thing that we can do is compare actual summarization systems with both of those bounds. Okay, so here's an example. I use a slightly different visualization because I want to compare many different rounds. But again, we have 5 to 90 summary. We have the lower bound, which is this pink line here, random. It starts in this particular set of queries. It starts at 65 or 64 for random, and to 90% it goes way up. And you would expect that. If the judge agreement in this case starts here and then goes up, it goes up monotonically, as you could probably also expect, and we actually confirmed this in our experiment. Now, what is interesting is that different summarizers actually do differently, and they all fall into this range. Now, this metric actually doesn't show an advantage for lead-based summaries. And lead-based summaries in this case are the ones in focus. So for the interesting compression rates, which are 5, 10, and 20%, we have at least one of the summarizers here, WebSum and leads, that does better. And actually, the lower compression rates, both of them perform better. Then for 80, 90%, we have roughly the same performance. So lead is a little bit better on this one. Now, unfortunately, due to an error of mine, we did not get 50 to 90% in WebSum, and I really don't know if that would be higher or lower in this range. So that's only which we need to finish. But again, the interesting rates which are believed from 5 to 30, at least according to this consensus in the summarization literature, both WebSum and lead outperform lead-based summaries. Okay, the next interesting thing that you can do with relative utility is do the same experiment in multi-document, with multi-document extract. So in multi-document extract, we have again a random. So again, I always use as the x-axis the lowest random. So random goes from 61 for 5% compression rate to 69 at 30% compression rate. This is done on an average of 10 classes. That is a total of 10 multi-document extracts of 10 documents each. In this case, the inter-judge agreement is this purple line, and very consistently with the way with what Kappa showed, when you have multi-document summaries, the performance of the summarizer is relatively much better than the case of single document summaries. In this case, actually, for 5%, it's just slightly higher than inter-judge agreement. And in the other compression rates, it's within small margin. Okay, so I think it's time for a break. We have one more set of evaluations, and then we have some general thoughts and a conclusion. And according to Sanjeev, this is probably the right time to have a break. So if you have any questions, go ahead. Otherwise, let's have some coffee and then come back. No more than 15 minutes, please.